はい、それでは時間となりましたので、セミナーを開始いたします。本日座長を務めますのは、九州大学アジア・オセアニア研究教育機構創発推進コーディネーターのキム・シューマハー、准教授です。それではキム先生、よろしくお願いいたします。
Dear Lee Sensei, thank you very much. I welcome everyone, all the participants in today's Brown Bag Seminar, the 132nd edition of the Brown Bag Seminar. And today we will talk about something extremely relevant for two very important SDGs, clean water and affordable and clean energy, because today we are very pleased to welcome Associate Professor Osama Eljamal, who will present, who will talk about energy recovery potential from wastewater and integrating nanotechnology into the recovery system. So a little bit of background. Professor Eljamal is an associate professor of environmental engineering in the Interdisciplinary Graduate School of Engineering Sciences at Kyushu University. He obtained his undergraduate degree in civil engineering from IUG in Palestine in 1997. He also received his master and PhD degrees in environmental engineering from the Graduate School of Engineering at Kyushu University in 2006 and respectively in 2009. He joined the Department of Earth Resources Engineering at Kyushu University as a JSPS postdoctoral fellow between April 2009 and October 2010. After that, he secured several different positions, first as an assistant professor at the Graduate School of Bioresource and Bioenvironmental Studies at Kyushu University. And then afterwards, he was promoted to associate professor, or his current position in the Interdisciplinary Graduate School of Engineering Sciences at Kyushu University in 2014. He joined various other universities, either as a visiting professor or as a fellow, including the University of Waterloo in Canada and the University of Oxford in the United Kingdom. So with that being said, with this impressive background, I'm again very pleased to welcome Professor Osama Eljamal. Professor Eljamal, the floor is yours.
Yeah, good morning, everyone. Thank you, Professor Kim, for the nice introduction. Can I share my slide now?
Yes, Osama Sensei, please. Yes.
Can you see now? Okay.
Perfect.
Oh, thank you. So again, thank you for the invitation, and really I appreciate your effort as a group of the Brown Bag Seminar, because I believe this is a fruitful, seminar series of seminar will improve the connection between Kyushu University and other researchers worldwide. So as Professor Kim mentioned, my topic today, I will talk about energy recovery potential from wastewater and integrating nanotechnology into that recovery system. So briefly, I would like to introduce my research laboratory, which is Water and Environmental Engineering Laboratory. We call it WEEL. And in this laboratory, we have two types of research activities. One type focusing on the water and wastewater treatment to recover or to recycle the water for our system. And in this other side, we focus on the bioenergy production from the organic waste, which is released from the wastewater or other agriculture or industrial activities. So why we focus on the water? Because we believe water is the source of all life. Without water, we cannot survive in this earth. And day by day, the demand increasing for the water due to the population increase, industrial activity, agricultural activity, as well as the lifestyle of the people need more and more water when they change to the developed and use some new technology. At the same time, we discharge too much wastewater after using, and the problem of this discharge wastewater is a main source of the contaminant to our environment, including the surface water like river water or lake water, even seawater. And the problem is increasing day by day, and United Nations, for example, World Health Organization reported that in 2019, more than 144 million people drinking some contaminated water with different contaminant, of course. And then we believe that water treatment is necessary to first overcome the deficit problem of the water by recycling and reusing the wastewater. And the second is to protect our environment from any contaminant released to the environment through the wastewater system. So in this part, we focus in the application of nanotechnology to improve the efficiency and to accelerate the system to get more efficient treatment and speed up the system. And in the other side, as I mentioned, energy also one of the important part for our life. And same like water situation, day by day, increasing the demand due to the population, lifestyle, industry, agriculture, activities, and so on. And at the same time, the problem in the non-renewable energy, very shorted non-renewable energy, and we facing some accessibility to non-renewable energy due to some global conflicts. And most of the energy now come from the fossil fuel, and we know that is the source of the carbon dioxide and some greenhouse gases. Due to the industrial revolution, more than 40% of the CO2 released to our atmosphere, and that make environmental issues globally and create a global warming problem and other problem at the same time. So we believe renewable energy, one of the alternative and the opportunity to recover the deficits of energy and to reduce the emission of the CO2 and other gases, like, for example, wind energy, solar energy, geothermal energy, and other type of energy. In this part, we focus more in the biomass because we want to recover this energy from the wastewater and organic waste. In the same time, also we apply the nanotechnology to improve the efficiency of the energy production and accelerate the process in the system. So if we can imagine the system, the water and wastewater system for the urban area, usually we have water resources. Whatever these water resources come from the river, seawater after distillation, lake water, groundwater, then we need to use some verification to treat and clean that water. Then we have to construct a water distribution system. The water will be distributed for homes and industry. From homes, later the homes will discharge the wastewater, which called domestic wastewater or local wastewater, which mainly rich by organic matter. In the other side, industry zones reproduce and discharge industrial wastewater, which is rich by different type of contaminant, including heavy metal, Newton, and so on. We need to collect this wastewater and treat this wastewater before discharge to the environment. Otherwise, it will be source of contaminant. But at the same time, this system need time, effort, money, very cost system if we want to work perfectly. So we believe by adopting some recovery system inside the treatment system of the water and wastewater system, it will be a good idea to minimize the cost and get some benefit even. So the wastewater can be adapted through the treatment system to go with first treatment of the water to recover the water totally from the wastewater, which can be later applied for irrigation, agriculture activity, and also nutrient can be recovered through that system, which can be applied for agricultural activity as a fertilizer. Then from this side, we can produce food and we return back this to the human being as a source of food. In the other side, energy can be recovered from the wastewater by degrading the organic matter and produce electricity, and which can be returned back to the industrial as energy or electricity. So applying this concept, we can totally get some benefit from the wastewater. Instead of considering wastewater as a waste, can be resource. So what's the problem with the wastewater? Because we have some huge city, some huge urban area generate a huge amount of wastewater in the small area. So then this huge amount of wastewater make or cause some several problem to our ecological system. And if we discharge this wastewater without a proper treatment, it will be a big source for contamination to contaminate our environment. So it seems likely 80% of the wastewater which release into the environment sometimes without a treatment or sometimes without sufficient treatment. That is really big issue in the worldwide. And why this is sometimes does not work? Because the treatment and transport of the water and wastewater consume too much energy, almost 1 to 4% approximately of the total electrical power. For example, in United States, about 3%. That means very costly comparing with the benefit getting from this system. So some city or some country, they ignore to work on that system. But we have to remember domestic wastewater contain approximately 99% of water. So this is water, and there is a 1% only include the organic, inorganic matter suspending or dissolved solid, as well as microorganism, bacteria, and so on. So due to this 1%, we need to treat this wastewater before discharge it to the environment. And we have to believe that wastewater 99% is water. And only due to this 1%, we called it wastewater. By removing this 1%, we can call this water. So it's become a resource for our life, not waste. So typically we use different treatment technique or technology to treat or to remove that 1%. Physical treatment, chemical treatment, and biological treatment can be applied to remove the 1% of the organic matter and other chemicals from the wastewater. The typical composition of the wastewater usually has 20 to 85% milligram of nitrogen component, 4 to 15% of the milligram per liter of the phosphorus component, and about 80 to 290 milligram per liter organic matter. And here is the organic matter is the store of the energy. We can convert this organic matter into energy by using and applying some technology. As I mentioned, the economic development and demographic growth make too much pressure onto the demand of the fresh water and energy. And the production of the annual wastewater estimated to be 4.5 multiplied 10 power 11 cubic meter by year. And this is very huge amount of the wastewater. By recovering the water and apply it through an irrigation system, nutrient as a fertilizer for agriculture, biogas as energy, we can get some benefit from this one. Usually, we evaluate the wastewater by these two main parameters. We call the first one biological oxygen demand, BOD, and chemical oxygen demand, COD. So most of the people, they think about those two parameters. They evaluate how much the wastewater is contaminated by organic matter and how much the wastewater is a problem. So when the BOD and COD increase, we consider this is true waste. But in this side, we can consider the BOD or COD as an evaluator for the amount of organic matter which is equivalent to the energy stored inside the wastewater. So we have to look to the BOD and COD, not factor or parameter represented the waste and the problem. It's represented the energy stored in the wastewater. So we try to work in two systems here to recover the energy. Actually, there is a potential of energy in wastewater, could be about 10 kilowatt hour for each cubic meter. And in the wastewater treatment system, we consume less than 1 kilowatt hour for cubic meter. So that means, by another word, we have energy stored in the wastewater 10 times greater than more the energy needed to treat the wastewater. So if we able to recover part of that energy, we will recover the cost of the treatment and maybe get extra energy. So in this regard, we apply the anaerobic digestion system. We try to improve the anaerobic digestion system to get much more methane or hydrogen from that system, which can be considered as a biogas for energy. In the other side, we apply also microbial fuel cell to produce the electricity directly from this unit and in the as a byproduct hydrogen gas. Both is kind of energy. So anaerobic digestion, this is, by the way, just a picture of the anaerobic digester, which is located near to Hakata area, Takeshita station, maybe very close to Takeshita station. And in the anaerobic digestion, inside the reactor, the mechanism work like that. The microorganism, the bacteria, degrade the organic matter which exists in the wastewater and convert that organic matter into biogas with absent of the oxygen, because this is anaerobic digestion system without oxygen. And then we have gas produced from this anaerobic digester. After some purification process, we can apply this gas as a source of energy to produce electricity, or maybe applied to some car, like hydrogen car or methane car, and so on. On other side, we have some byproduct produced from this one, which is concentrated organic matter, can be considered as a biofertilizer to improve the soil and enhance the agricultural production. So we can get both sides. So typically, the biogas produced from this system contain about a range between 50 to 70% of the methane, 25 to 50% carbon dioxide, 5 to 10% hydrogen, and some nitrogen gas, less maybe than 2%, and some traces like hydrogen sulfate. So we consider the methane as a valuable part of the biogas because we can convert methane as to energy directly, and also hydrogen become valuable because there is too many applications now for hydrogen as a clean energy. So in our study, we try to improve the production of methane, either production of hydrogen as an energy source, and reduce the production of the CO2 from the anaerobic digestion system. So I just want to share this study. We conducted this study in 2022. And in this study, we tried to improve the anaerobic digestion system by integrated and applied some iron nanoparticles. And we have pure iron nanoparticles, and at the same time, we have coated iron nanoparticles. And we try to investigate and understand the interaction between those nanoparticles and the system itself, which is contained the wastewater microorganism and so on. It's too complicated inside, but we tried to classify the mechanism inside. by the end of this study, we able to improve the methane production more than 120% comparing with the normal system, control system. So it was very good achievement using this coated iron nanoparticle to improve the methane production more than 120% from the system. For example, this is the figure showing how much the biogas in total improved when we apply just 0.5 gram of the coated iron nanoparticle. So we got improved in the biogas production 95% comparing with the control or the normal system. In the other side, the methane produced from this system increased to 122% comparing with the control one. So this mechanism or this nanotechnology not only increased the biogas to 95%, but also increased the percent of methane inside the biogas more than 13.8% comparing with the normal way. So we able to increase the biogas in total, and we also increase the methane content in that part. So this study, too much details and information has been published in the Renewable and Sustainable Energy Review Journal in 2022, actually, under this title, A Novel Method to Improve Methane Generation from Waste Sludge Using Iron Nanoparticle Coated with Magnesium Hydroxide. We also apply the concept of the nanoparticles to recover or remove the phosphorus as a nutrient from the water, and we simulate the situation of the permeable reactive barrier, which is kind of barrier can be constructed to treat the groundwater from the contaminants. So in this case, we apply several scenarios to introduce the nanoparticle into the permeable barriers. We use, for example, injection. We use one layer of our nanoparticle, two-layer mixing, and actually more than 12 scenarios to find the best way to introduce the nanoparticles into the permeable reactive barrier to remove the phosphorus in this case, and maybe in other case, we can remove different contaminants. So in this study also, we clarify the mechanism of the removal of phosphorus from the groundwater using the bare iron and the bimetal. We here apply different iron nanoparticles, which is iron with copper, and we call this one iron copper bimetal. So we clarified all the mechanism to remove the phosphorus from groundwater through this study, and we found that the injection is the best way to deliver the iron nanoparticle into the system to remove or to recover the phosphorus from the system. And this information also has been published actually in the Journal of Molecular Liquid in 2020 under this title, Investigating the Design Parameters for Permeable Reactive Barriers consisting of nanoscale zero-valent iron and bimetal iron copper for phosphorus removal. Actually, we work in this project along with the Professor Ian Thomas from the Department of Engineering Science, University of Oxford, United Kingdom. So on other side, this is another example how we can recover the energy from the wastewater or organic waste. The previous one, it was like anaerobic digestion system, closed system to produce biogas. But here we will talk about microbial fuel cell, which is a device can produce electricity by degradation of the organic matter which exists inside the wastewater. So the concept of this device is very simple. We have a two chamber. This chamber, we call this chamber anode chamber, and this one is a cathode chamber. And between those two chambers, we have special membrane separate the two chambers. Another side, we have the anode inside and connected with the cathode side using the circuit, electric circuit. So what happened here in the cathode anode side, we supply the wastewater, which contain the organic material, and the bacteria degrade this organic matter following this biochemical reaction and they produce electrons. So the electron will be released and flow through the circuit. We get the electricity from this way. And also the microorganism or bacteria produce the proton, H+. The proton will pass through this special membrane to the cathode side. The electron and the proton meet in the cathode side with the existence of oxygen and forming H2O, water. So by another word, this device can produce electricity from this side and water from this side. Both is environmentally friendly, but we have to remember CO2 also can be produced from the cathode side. We have to work to reduce the CO2 production from this system. So in this study, we try to improve the efficiency and accelerate the electricity production inside the microbial fuel cell by introducing the nanoparticle into the anode side to improve the production of electrons and the proton and increase the degradation process of organic matter or wastewater. So we apply several types of iron nanoparticles and nanoparticle engineering. We usually characterize those nanoparticles using several devices actually to understand the chemical and physical properties of those materials, because this is very important for us to understand those things, which is useful and helpful to understand the mechanism and the interaction with the either anaerobic digestion system or microbial fuel system. So this is just a simple example from the image which taken for those nanoparticles by the transmission electron microscopy, but actually we use XRD to characterize. We use same scanning microscopy, FTIR, and several devices to understand those particles. Anyway, we apply this particle into microbial fuel cell, and with different conditions, with different scenario, we optimize and operate those microbial fuel cell for a long time. And then we got a good achievement, good result from this operation. We were able to improve and increase the voltage 441% comparing with the normal control one by adding some iron magnesium coated particles. And at the same time, this system also improved the removal of the organic matter from the wastewater inside the microbial fuel cell 25%. So we got here two benefits. One is improving the removal of the organic matter and increasing the production of electricity inside the microbial fuel cell. Too much details actually, because we investigate several parameters, several factors. We optimize those things to get the electricity and reducing the organic matter. And this information has been published with too much details and in the Energy Conversion and Management Journal in 2021, actually, under this title, New Insight for Electricity Application in Microbial Fuel Cell, applying magnesium hydroxide coating iron nanoparticles. Actually, this is just, how can I show? Two examples from our work. We have many studies have been done with these two technology, either anaerobic digestion or microbial fuel cell, or another side with water and wastewater treatment using nanotechnology. But today I just summarize within two examples. And before finishing my lecture, I would like to let you know, actually every year in October, my lab, Water and Environment Engineering Laboratory, along with the School of Engineering Science in Kyushu campus, you have to remember, We are located in Kyushu campus, not Ito campus. Organizing an annual international exchange and innovation conference on engineering science every year in October. This year, for 2024, the conference will be held in 17 and 18, and the deadline to submit the paper is July 31st, and registration is free because this is sponsored by our school and our lab, so we don't need to collect any money from the participant. And also this conference is a Scopus indexing conference, so all the publication will move from this conference to the Scopus system. And actually, this is the QR code of the My Lab website. If you're interested to know more about our research activities or our team, you can just scan this code and get more information about the Water and Environment Engineering Laboratory. And that's all. Thank you so much for your kind attention. So please.
Thank you very much, Professor Eljamal. This was very interesting, and I think it's a very relevant topic for a lot of people in the world, because, as you said, like both energy and water are some of the things that we definitely need to conserve, and that we also need to find ways to expand it to a lot of people. With that being said, I first would like to invite now people to ask questions if they have them. Please do post your questions in the chat. They can either be in English and or in Japanese. So please do post them. If they are in Japanese, I think one of the moderators will also help with the translation. So please do post your questions, if you do have questions, in the chat to Professor Eljamal. So let's wait a little bit for people, because I think it was quite technical. So I would first wait a little bit. If not, then I will ask also questions. So if there's any questions for Professor Eljamal.
Yeah, we have, sorry, I'm not sure, Mike, okay. We have a question now from, I think, Professor Rumiko.
Oh, Yokota Sensei, yes.
Yokota Sensei, he mentioned here, kindly tell us a bit about main challenges with the technology such as an revitalization system and microbial fuel cell. Are these systems already commercialized, or if not, how long more will it take to be
Commercialized?
Yeah. So thank you for the question. I think this is the most important question, because we need to see something, working. As engineering, we have to make the thing working, not just in the research part. So actually, anaerobic digestion system is working now everywhere. Many in Japan and many countries, they have anaerobic digestion system to produce methane, and they use the methane to recover the part of energy of the wastewater treatment plant. But with this nanotechnology, still there is no system. Actually, before COVID-19, we have planned between my lab and Oxford University and one Japanese company to apply this nanotechnology into the anaerobic digestion system. But within COVID-19, everything stopped. So hopefully, soon they will, think again about that technology to be in the large scale application. So far, there is no large scale application of anaerobic digestion system based on the nanotechnology or nanoparticles. But of course, anaerobic digestion exists in everywhere almost. And for microbial fuel cell, it's more difficult because still this device a little bit expensive because the construction of this device using some membrane, some anode cathode material is still a little bit expensive. And we're working to reduce the cost of the construction and at the same time to improve the efficiency and accelerate the process, which can be sufficient to recover the cost of the construction, and we can get some extra energy. Yeah, there is some challenge, but I believe for anaerobic digestion may be within 5 to 10 years, this technology will be applied, maybe in many cities. But for the microbial fuel cell, I think more than 10 years still need more research and more investigation to improve that. Yeah. Thank you.
I have a question that goes into the same direction because that is something that I've followed a bit, and I do think there's an overlap, and you can either confirm or disconfirm so does your research also go into what is recently, so I've seen like plants in India but also in other places that are heavily bogged down by plastic waste, which often ends up in the waterways. So can your research function also in the context of creating, for example, fuels from waste? So, for example, next generation fuels such as, for example, transforming plastic waste into fuels again. So does that go into the same direction, or is that a completely different process, or do those processes partially overlap?
Yeah, this is a technical and deep question actually, because this is this stage which you mentioned is intermediate inside the process. So inside the process, bacteria convert the organic matter into some monomers or polymers, which can be used to later to generate the energy like oil, or maybe fabricating organic plastic matter, something like that. But in my study, actually, we jump this intermediate one and we go directly to produce the biogas and the electricity. And recently, we changed really our focus. Instead of increasing the methane production, we try to increase the hydrogen production in the anaerobic digestion. As I mentioned before, we are able to increase the methane production, and maybe, but still methane is, when we use methane as energy, it will release CO2 as well. So if we go to the hydrogen, hydrogen more friendly, it will release H2O instead of CO2. So now we're focusing more in anaerobic digestion system to optimize that system to produce hydrogen, which is more clean energy. And in the microbial fuel cell, we also focus to produce electricity, and in the byproduct through the system, we believe hydrogen can be produced. Already hydrogen produced, but with a little amount. But we want to modify and optimize and improve the system to produce hydrogen instead of CO2. So this is the target. So I think your point is some point intermediate. It can be work, but still we didn't focus on that part because our target is energy, direct energy. Yeah.
I see some other questions. So from Yamauchi-san.
Yes, Yamauchi-san, he mentioned iron cover bimetal nanoparticles. I think he mean seem very active and stable and costly. These are realistic for application. Yeah, the question is good, but you have to remember that cost not evaluate just directly how much that cost, because you mentioned here is very active. So when we use iron and iron covered bimetal, we increase the reactivity, we increase the efficiency of the system. So increasing the efficiency of the system, that means increase the production, increase the benefit. So we have to evaluate how much we invest if we use bimetal, iron cover, and how much we invest if we use iron only, and how much we will get benefit. So actually, as you mentioned, iron cover bimetal more expensive than the iron alone, but the efficiency increased too much. Then we can recover more than the cost. This is the point. So not all the time we have to look just to the material itself. We have to look to the production. Even the material expensive, but we have some, valuable output from the system. Then we consider this material is not cheap because we not expensive because we recover the cost of the material and we get extra benefit from the system. Yeah, good question. This is economic analysis for the system. Actually, we conduct that study to see the economic value when we use this material. Thank you for the question, Yamaguchi-san.
Okay, and with that, we have reached the end of today's session. We're already 1 minute over, so you can see there was a keen interest in your presentation. And thank you for all the detailed explanations and your answers. So if people do want to reach out, as was shown, the QR code, you can also access the slides on the website. Currently, we're experiencing some issues with the website since there was, I think, like an outside attack on the servers, but that should be repaired. So do take a picture right now if you want to learn more about his laboratory and also some of the activities that he mentioned. And then please do reach out to him if you do have questions. So thank you once again, Professor Eljamal. Very interesting stuff. I might even reach out to learn a little bit more, especially what I mentioned with waste, because again, I'm not an expert in that field, but it is something that I have a keen interest in. So thank you very much. And then I will now hand it over to the Q-AOS members to present next week's BBS. So thank you once again, and I hope you have an excellent day to everyone.
Thank you.
はい、小様先生、またシューマッハ先生、本当にありがとうございました。とても興味深い、講演内容でした。ありがとうございました。最後に事務局よりご案内させていただきます。まず、次回のブランバックセミナーのご案内でございます。次回は、来週2月28日水曜日12時10分より、九州大学アジア・オセアニア研究教育機構、E. ジョンソン、学術研究員より、ゲーム理論と国際関係と題し、講演を実施いたします。これ私なんですけれども、詳細はホームページをご覧ください。